Good evening, all. So today we are starting the next session of our training session of ISO. And today we discussed about the measurement of distance, and today we will be discussing something else regarding the composition of stars or something like that. How do we measure what is there inside a star or in a planet or something like that, and how fast, whether it is moving towards us or away from us. These kind of things will be discussed today. Okay, so with further ado, let me share my screen. Yeah. Oh, this is visible. And a brief intro of what we have learned last day. We were discussing the measurements in astronomy, and we know that all this happens with analysis of light, and light means there are different kinds of light, that is starts from gamma rays and extending up to radio waves, and only a small part that is visible light, which is visible for our human eye. And not all the lights are actually receivable on the ground surface, because atmosphere is opaque to gamma rays, X-rays, and ultraviolet, and some of the infrared and microwaves as well. So for observing in those regions, we have to go to space. That is why we have space telescope. And then not just the light, there are other kind of waves are also there, or other kind of things like gravitational wave, neutrinos, and cosmic rays are there for observing the cosmos. Okay. Then we discussed about the measurements of distance from light. Okay, so that is why we do have something called the cosmic distance ladder, because to measure the distance, each range of distance, we have to use a proper method for them. Each of them is better to be measured, or each range should be measured with a proper distance measurement method. Then only we get the accurate result. So for that, for the nearby system, we have ranges like arranging like for solar system. Then beyond that, we have parallax method, and even beyond that, we use main sequence floating, which I haven't explained in detail because HR diagram you have to learn later. We will discuss later. Then Cepheid variables and the wide dwarf supernovae we discussed, and the Hubble's law, the usage of Hubble's law for measuring the distance, that we will learn later. Okay, so these are the this is called the cosmic distance ladder, and we discussed the parallax method, where we observe a single thing with from two different places. Okay, something like maybe around the orbit. Okay, 2 months, 6 months apart, we are observing the same object, and we are measuring how much shift is there when we are observing those stars, and from that shift we can calculate the angle P here, and that angle is called the parallax angle. From that parallax angle, we can actually measure the distance to those objects. Okay, this is the summary of the parallax method. And the next one we learned is the flux luminosity method, or the standard candle method, where luminosity is defined as the total amount of energy emitted by an astronomical object, and flux is the amount of energy that we received here per unit area, per units per second, or what is the energy, that is what is the power that we receive here per unit area. So flux and luminosity, we derived an equation, so simple equation, that is flux and luminosity are connected through the distance, and from that equation we can find out what is the distance. So if you know the flux and luminosity, then we can find the distance. That is the idea of what is called the flux luminosity method, or standard candle method. So you need to know the flux, that is measurable, and you need to know the luminosity, which is not that easy. But if you know both, then you can easily find out the distance. So that is the idea of the standard candle method. So what I mean by that standard candle here, so standard candle is the object for which we already know the luminosity, or the energy actually emitted per unit per second already, without the knowledge of distance. So there are some objects are there in the universe for which we know the luminosity from other parameters, like for example in the case of Cepheid variable stars, from the periodicity. So Cepheid variables are regularly pulsating stars, so its period is varying, or its brightness is varying at a regular period or at regular interval. So if we know that interval, from that interval actually we can get its real energy emitted. So we know the real energy emitted, observe it with a telescope to get the flux, then we can connect it using, or from that flux and the luminosity we can calculate this. So another object was the type 1a supernova. All the type 1a supernova has the same, at its peak brightness, all the type 1a supernova has the same intrinsic energy, or all the type 1a supernova has the same energy output when it is at the peak brightness. So from that actually we can estimate the energy of the type 1a supernova, then that means the luminosity. From that we can actually find the distance. So another standard candle is actually type 1a supernova. So that is what we were discussing. Now we are going to discuss another topic called spectroscopy. Okay, so spectroscopy is a general branch of physics, or maybe in chemistry also it is applied, where it is mostly used or mainly used to find out some unknown elements or what are there. It is not just for elements, or in practice it is actually applied for to find out what molecules are there, maybe water content is there, so something like that. So any molecule, any atoms, all these kinds of thing can be found out using what is called the spectroscopy. So that is a major branch in science. Okay, so let's see what it is. Before going to that, let's learn what is a dispersion. Okay, so take the first figure here, that is a prism. I don't know whether you are familiar with it. It is actually a 3D object which looks like a tent actually, but it is not big as a tent, it is a small thing. So when a light, okay, when usual sunlight or some white light is passed, so white light has a meaning else, but now just take it as a sunlight. When sunlight is passed through that prism, the prism has the ability to split that light into its constituent colors, so or what is inside that light. So usually when you take a normal light like the sunlight, we feel it as a single color, or maybe we feel it as some white or yellowish color maybe, but actually when you analyze it using a prism, actually it consists of many different colors. So we can call it as a composite light. So sunlight is not a single light, it is actually a composite light. So composite lights are usually called the white light, or simply we can call it as composite light. So it is a composition of different colors, or instead of different colors we can say that different frequencies. Okay, so color is actually different frequencies as well. Okay, we can say that it is red has a special frequency, and each of this color has a special frequency. Okay, so these are different frequencies that we have, and each color is a frequency, or we can say that it splits into different colors. Or more specifically, if you want to say, when a composite light is passed through a prism, it split in or arrange it into its constituent frequencies, or what are the frequencies inside that. So if you are going from bottom to top, then it is like in the decreasing order of frequency, it will arrange like that. Okay, so either if you want to say, call it formally, we can say that it splits its constituents into different frequencies, or simply we can call it as it into different colors. And that splitting of that composite light by a prism into different kind of light is called the dispersion of light through a prism. So this phenomenon is called dispersion. Okay, so so the prism has this ability to split the composite light, so that we can understand whether there is how many kind of lights are there, or how many colors are there, how many frequencies are there. Okay, so that is one advantage. And suppose if I send a certain frequency, suppose a sharp red, something like a red laser light. Usually a red laser light means it consists of only a certain color, there is nothing to split. So if you send a red light through that, it will come as a red light itself. So there is nothing to split into. Okay, it consists of only a single color, okay, or single frequency. So it happens only for a composite light. It should consist of many different colors, then we can split it into different. If you send a single one, it will come as a single one. There is nothing obvious there. Okay, or there is nothing interesting there. But if you send a composite light, we can split it into different. So prism is one instrument or one device in physics which is capable of splitting the light into its composite uh, colors, and that phenomenon is called dispersion through a prism. Okay. Now, prism is not the, and one more interesting thing, you know that you will see this color in a rainbow as well. So rainbows also works on the principle of dispersion. So instead of a prism, the water droplets in the atmosphere, tiny droplets, they will act as a prism. When the light comes through this, it will come and the white light or the composite sunlight will come and go exit like this. So during this exit, it will split into its constituent colors, and it is causing the what is called the what is called the rainbow. So it is not just a single water droplets. There should be billions of them or millions of them should be there, and they are together causing the rainbow. Okay, so that is how a rainbow works. But anyway, that is based on dispersion. But to split the light into its constituent colors, there is one more method in physics, or there is one more instrument. That instrument is called a grating. Okay, that is called a grating. So grating is actually something so simple. Just leave the CD right now. So take a glass, okay, a transparent glass, and draw lines on them. Okay, you can score with some hard material, or you can print something on that, so that these lines are opaque and the space in between the lines are transparent. Okay, because the glass is transparent. Wherever there is the line, it is actually opaque. But it is not that easy. You may think that you can draw it, you take a paper and, or not a paper, take a glass and you can draw it easily. But when you closely look, there should be at least some to 1000 or 2000 lines per every centimeter. So within a centimeter, you should be able to draw some 1000 lines. So it is not practical simply with the method of drawing it regularly, but there are some other methods for making grating. So now if you make a glass like that, and when the light passes through this, okay, when the white light or the composite light is passed through this, it will again split into different colors. So this is the second method in science, in physics, that to split the light into its composite colors. Okay, so the purpose of splitting we will discuss later, but anyway, by splitting we can at least understand what are inside that. Okay, so from a single light we can split it into different means, we can find out what is inside. Okay, so that is one advantage. It is something like we are dissecting the light to see what is inside. So grating is one example, one another thing. And for astronomical purpose, nowadays people use grating instead of prism. So grating is better technology, and grating is working not on the principle of dispersion, it works on a principle called diffraction. Okay, there is another scientific an optical phenomenon called a diffraction. So grating works on the principle of diffraction. Then why there is a CD in this slide? Because when you look on the surface of a CD, you can see this rainbow of colors like this. You see these colors. Okay, in the CD has an ability to split the colors into or split the light into its constituent colors. Okay, so how it is happening? Actually, this CD is also a kind of a grating, because if you zoom into a CD, actually the writing, the data writing in that CD happens through tracks. So it consists of so many tracks, something like a ground or something. You can imagine so many tracks are there. It is so tiny we cannot see normally. So it is something like at the molecular level there are tracks. So those tracks act like a grating, and by that grating there is this diffraction will happen, so that the color will split into its constituent colors. Okay, or the light will split into its constituent colors. So we have two instruments. One is prism. So this is the first one. Okay, so first people discovered this prism, and later they discovered this grating. So we can use this both, but nowadays the grating is the one used in all the professional telescopes, where people are using grating for splitting the light, because it is more efficient and you can split even more, or it is something kind of now, for example, in this case, for a for a prism, if it's split in this wide, actually if it is a grating, I can split it more, or I can make it open wide, so that I can even see what is inside each of the frequencies. So it has more resolving power or more resolution. So that is why gratings are being used. Okay, so that is about the So this method of splitting the light into its constituent colors and analyzing it is called a spectroscopy. And for analyzing this light, we need an instrument, and that is called the spectrometer is there, or spectroscope is there. It is usually called a spectroscope, but when you record it one by one using a computer and all, it is called a spectrometer. So in all the professional telescopes, the light is not just taking into a photograph. It is happening obviously, but apart from that, it is actually connected with a spectroscope or a spectrometer that will record the spectra of that light from a star or something, whatever we are observing. And that means it is splitting it into its constituent colors. Now, before going to that, we have to learn there are different kind of spectra are there. Okay. So spectra means it is the arrangement of those constituent colors. That is the meaning of that spectra. Okay, it's a collection. Now let's do the same experiment for different objects. Okay, first of all, we are going to take a hot object. Hot in the sense we can heat things so that it glow. Something like if you take a nail in front of a gas light or something, eventually it heats up and it will glow like a red hot or something like that. That means we are heating it up and it is giving off light. Okay, so something like that, you can take some metal, something like a tungsten filament inside a bulb, and it is heating up. And when you send that light through a prism, it can be either a prism, okay, or a grating, no problem. Anyway, something to split the light, okay, into its constituent colors. Then if you send that light through that prism, it will split into its colors. There is nothing obvious that we already mentioned. And when you look into this, you can see that if it is not a gas or anything, it is actually a metal that is heating, okay. And then you get a continuous spectrum. You can see that this is continuous, okay, continuous spectra. Why it is called a continuous? Because there is no break at all, okay. I will show you why this name, because there are spectra which has breaks. Okay, anyway, you can see that it starts from one color and ends at another color. The brightness may vary bit by bit, but it's anyway, it is almost uniform. Okay, all colors will be present. Now, if I take a gas, this is not sun, okay. Actually, I should have been used another shape. People think that this is sun, but this is not sun. This is a hot gas, okay. So we are taking a gas or a vapor of something inside a tube, and we are actually heating it up using some electricity, so that the gas get heated and gas will glow. So when that gas is glowing means it is emitting light. That light can be fed into a prism again, okay, and that light again shows up something like this, okay. So here you can see that when I split it, there is no continuous light, okay. You can see one light here, one light here, one light here, one light, but you won't understand it from the direct light here. But when we send it through the prism, we can directly see, yeah, these are the light that is present inside. These are the only lights. There is no continuous thing. So this is a discrete thing. It is not continuous, and this is called emission spectra. Okay. So why it is called emission, I will explain later. Anyway, it is called a emission spectra. Okay. So emission, it has a reason for that I will explain later. Don't worry. So that is it. Okay. If it is a hot gas, so some gas is heated to a high temperature, then it is glow. Then that light will be giving some certain lines, certain fixed lines. Okay. So and it is called a emission spectrum. Now let's take the same continuous light. So we know that this incandescent bulb will give you a light like this. Okay, you can a spectra like this, a continuous spectra, and we are feeding that, or we are allowing to pass that light. Okay. Oh, before that, I will give you another example of this hot gas. So hopefully you might have been seen this thing, this street light with an yellow color. So in that yellow colored lamp, actually that lamp itself consists of a tube, and that's a bulb basically. So inside that bulb, they are filled with the sodium vapors. Okay. So the sodium vapor is there, and that is heated up by electricity. So when it is heated up, it will glow. And due to that glow, there will be different colors are actually coming, and that is an emission spectra. You can see it consists of many colors from here to here to here to here. All these colors are there. but out of which you can see these two colors are so bright. Okay, see these two colors are so bright, and they are called the sodium lines. So it is a unique thing about the sodium, and they are called the sodium D lines. Okay, and that gives that sodium lines or that bright yellow lines are actually giving that appearance for the street lights. Okay, so that is called the sodium D lines. Now let's go and see. Okay, so that is one real life example, and if you fill it with the neon, magnesium, or different kind of things inside that tube, it will give you different colors as well. Okay, now let's see the next experiment. We are actually passing that incandescent bulb light through a cold gas. So this is a cold gas, not a hot gas. Okay, so when actually this light, okay, the light from this bulb actually consists of all the colors continuously. There is no breakage like this. Okay, light like this. Now we are passing it through a cold gas. Now some light will come out, but we cannot see any difference if you look at here. But if you send that through a prism or a grating, it will split into its constituent colors, no doubt at all. But when it is splits into different colors, there will be some absence of colors. You see, some missing lights are there. Okay, and this kind of missing spectra, okay, the missing lines from a continuous spectra, and this kind of spectra is called absorption spectra. Okay, absorption spectra. So the first one is continuous because there is no breakage at all. The second one is emission. I haven't said the reason for emission, the name. Okay, anyway, just see the difference. What is the difference? Just understand that there will be only specific lines. Now absorption spectra, there will be certain lines are absent. Okay, so this is absence and this is the presence of only certain. Okay, here certain will be absent, here certain will be present. So now before we are going to understand what is there or what is the reason behind this, we will learn another thing. Okay, so why this is happening we will discuss later. But before that, what is the purpose of this, or what is so important in astronomy or in science? So not just astronomy, even in science. So you can see that this pattern, you can see that one line here, one line here, then after a certain gap there is another line, then after a long gap there is something here. Okay, so this lines, okay, this pattern, basically this pattern, not just the colors, actually this pattern of this gap, you can, if you notice the gap and all, that pattern is unique for us inside. Okay, so in previous case I have shown you the spectra of the sodium. That sodium spectra is unique for sodium. Okay, that similar kind of pattern won't be there for any other element in the periodic table. So it is unique for sodium. So another idea is that you can pass a light through a prism, an unknown light through prism, and analyze its lines, and we can say that whether that lines corresponds to which element, or whether it corresponds to hydrogen, whether it corresponds to helium or oxygen or neon, something like that. So that comparison can be made. Similarly, here also those missing lines, okay, depends on what is the cold gas here. So if it is a cold hydrogen, then that will be a special one, and this happens even for molecules as well. So you can take some solution and pass the light through this. Anyway, whatever the pattern is here, it is unique for what is inside this. Okay, so wherever you go in the universe and do this experiment, the hydrogen has a fixed pattern, the helium has a fixed pattern, the lithium has a fixed pattern. So all the elements in the periodic table has a fixed pattern, like a fingerprint. As far as we know, the fingerprints are unique, so we can call it as the fingerprint of atoms. And these lines are called spectra, not just spectra, they are called spectral lines. Okay, so these lines, whether it is this black lines called the absorption line or the emission lines, they are together called as the spectral lines. So we say that spectral lines are unique, or it's like the fingerprint of atoms. So once you have the fingerprint, the standard fingerprint of all the atoms, then whenever you get an unknown light, you can check whether this light is present or not in that light. Okay, if this pattern is there, then we can confirm that that element is there in that star or planet or wherever that light is coming from. Okay, so that is the idea of this. It is something like you are going to a crime scene where there are multiple fingerprints are there. You collect all the fingerprints and you have one or two suspects are there. Then take the fingerprint of the suspects and compare it with the crime scene fingerprints. Okay, then if you get a match, then we say that he might be a culprit or he is the one who commits that crime. Okay, so the similar way we can also kind of act like play like a detective and find out what is there. Okay, I will give you some example, and after that we will go to the reason behind this. Okay, for example, this is the spectra of sun. If sunlight is passed through that grating or a prism, so in a usual prism you won't be able to see these lines, but if you send it through a grating or something like that, then you can see these lines. Okay, forget about the naming and all, but you can see these lines. So some of these lines may correspond to, some of these patterns actually correspond to maybe to something like the, what to say, something it may correspond to hydrogen, something maybe to helium, something maybe to something else. Okay, so we don't know what it is there. Anyway, these lines may correspond to certain pattern. For example, this and this and this. So this pattern may be of calcium, so that we can say that in sun there is some calcium. And if you see this and this two, actually these two are actually the D2 lines of sodium. Okay, so we can say that this is the lines of sodium, so that sodium is present. So we can actually find out what is there in some unknown place or in an unknown star. Okay, because the prints are unique. So for example, you can see these are all the patterns or the fingerprints of helium, oxygen, neon, argon, xenon, etc. Okay, so you can see all these things. Okay, these are all the different patterns. Now in this pattern, if helium is present in one star or something, then there will be this pattern in that star, or in that star spectra you will be able to identify this pattern, not just the lines. Actually, if you find for helium, if you find two lines here, then after that certain distance these lines will be there, then after a certain distance this will be here. That gap is constant. Okay, so that pattern is constant. Whether the background color like this, whether it is blue, here it is blue, or yellow, or here it is green, that may vary, that we will get to that case later. But this pattern, that specific gap will be the same, and the thickness will also be the same. So that is how relative thickness will be also the same. So that is how we can say that it is unique. Now for example, in this here the first one is an unknown gas. I don't know what gas it is, but I have some standard. Okay, so this is the crime scene fingerprint and these are all the suspects. Now I can compare them. So compare with this. So I am trying to compare this line with this. Then if it is helium, okay, suppose this is helium, because I matched the one line, then if it is helium, the next line should be at this gap. Okay, but it is not helium because there is no line after this. There is no helium inside that. If there is helium, then another line should be here and another line close to that. I cannot find that pattern here, so it is not helium. So this is how actually I have to properly compare them. And now if I take another, I cannot find a corresponding line here or any lines like this here in oxygen, and neon I don't know, so these close by lines are not there. And if I properly match it, I can see that this line is here. Not with the one line I cannot confirm. From with the same gap I can find, you see these four lines are here, these four lines are here, and after the same gap I can find these two. Then I will take one more. Yes, again it is matching. So I can do it for the remaining as well, no problem. So I can identify this unknown gas is not anything else, it is xenon. Okay, so that is the method of finding an unknown element from the light. Okay, here we are not taking the gas actually. Here unknown gas means we are only getting the light and we are analyzing that light and finding. That is the advantage here. Okay, so without doing any chemical experiment or anything like that, you can get the light coming from a star or a galaxy or a nebula or whatever, and we can receive that light and find what are the missing lines there, and from the missing lines I have to find the pattern for each of the elements, and from those patterns I can find out whether it is or what kind of material is there, or what is the element that is present. So that is the advantage of using this method called spectroscopy. Okay, there is no need to go there, or there is no need to do any chemical examination. You can just analyze the light. So simple. Okay, because in astronomy what we receive here is only light. Okay, so the next one we can take it as this is the actually, but even I have represented the spectral lines like some beautiful colors and this absence of lines, but the actual result from a spectroscope or a spectrometer will looks like this boring graph. Okay, so this is one thing. When you go for space or astronomy, you have to think that astronomy or physics or astrophysics is not that colorful like the previous slides or anything. They are actually kind of boring graphs, data, tables like that. Okay, so don't fall in the colorfulness of astronomy, but it is colorful in a sense, that's for sure. But beyond that, it is some kind of this boring graphs are there. But once you learn about this, you can see. And from this also there are some elements are identified. You can see this line correspond to hydrogen, and this is also hydrogen. Then this is also hydrogen. Then this is helium line. Some along with that there is sodium, magnesium, oxygen. So this is actually what it looks. Okay, now this dip, okay, you can see that some is missing here. Some missing line means the brightness is less here. Okay, that is the missing line, but you cannot see something like this actually. Even the even if you use a proper spectroscope and look through that, observe through that, you cannot see anything beautiful like this. They will be very faint light and all. So this is just the representation to understand what it is. Okay, so now let's see why this is happening. Okay, so what is the reason behind this spectrum? Okay, why this spectrum is happening? Let's check what is the reason behind that. Okay, so before going to that, we have to learn something or just have the understand of just the basic understanding of an atom. So an atom, you can imagine it like this. It has a center core. That center core is called the nucleus, and as you know, it consists of two kinds of things, that is protons and neutrons. Okay, so that is the idea of an atom, and around that there are, so the concept of atoms and all, it actually differs. It is not just, it differs in the sense that this is just a model. The actual atom, we cannot have a specific path for electrons, but in one model we say that, especially for learning these things like the spectrum and all, we say that the electrons are orbiting in certain paths. So something like this. Now take, there is another path around this. Okay, and you might have learned this in your school class, and these orbits are called a shell. Okay, so these orbits of electrons are also called shells. Okay, and electrons can orbit in these shells. Okay, the spacing is actually different. The spacing is not same for all of them. Okay, let's see. So this is the first shell, this is the second shell, this is the third shell. So as you go outer and outer, its energy is higher. Okay, so this one has the high energy, this will have bit more less energy, it has the least energy. Okay, and you can imagine even there are many more actually, infinite number of lines are there. So don't worry about, there are many number of lines are, or paths are there, so that the electron can jump in between. So now imagine that there is a cold gas. Okay, so cold gas means its temperature is low. So all the, maybe many of the electrons, suppose it is hydrogen. If it is hydrogen, there are two electrons. Okay, so just take two electrons, and these two electrons are, since it is cold, the electrons are residing in the first shell. Now when a light is sent, okay, now we are sending some light to this atom, and those electrons can absorb energy from that light and jump to the next level. So it can jump, the electron can jump to the next level. Okay, so electrons can jump to the next level. So when it jumps from a lower level, that means a lower energy to the higher energy. So if you want to go from a lower energy to high energy, we have to get some energy. That energy is absorbed from light. So we get some energy, that is delta E, that is the difference in energy between these two shell, and it gets some energy and it will go to the higher level. Okay, so now just imagine where it got that energy. It got that energy from the light. So that specific energy will be absorbed from the light, and that energy corresponds to a certain color. So that is why, since the electrons jumped from a lower orbit to the higher orbit, it absorbed from some energy from the light. So that is why it is missing there. Okay, so that certain color or the energy corresponding to that color is missing. Okay, so again, the same one electron can jump from here to directly to the other one. Okay, the third one, so that it will absorb the energy corresponding to that. So when it is going from a lower energy state to the higher energy state, that electrons will absorb, not the word absorb, energy from the okay, that will absorb energy from the light. That is why some missing lines are there, and that is why it is called an absorption spectrum, because that missing lines happen by the absorption of energy or the colors from the light. Okay, so that is how it is happening. Okay, and one more interesting thing is that these electrons cannot accept any color. Okay, so it will absorb that specific color and jump. Okay, that is the property. And now we have learned something like the emission spectrum. So in that emission spectrum, instead of this hot gas, we have some, sorry, instead of this cold gas, we have some hot gas. So in the case of a hot gas, so let's take another pen to draw about the, yeah, in the case of that hot gas, the electrons are actually sitting at the higher orbits because of the hotness or the temperature. The electrons are at the higher orbits, and that means at a higher energy state. Now it can jump to a lower energy state like this. It can jump from 3 to 1. So high energy to low energy. So when it comes to the low energy, it cannot keep that high energy. So it has to give off that energy, and that energy will be given off as light or emitted as light. So it can come to this level, and it should emit the energy equivalent to this gap. Okay, and this is again this is called the energy, or this is the corresponding to this, there will be some light. So when an electron is jumping from a higher energy to lower energy, electron will emit energy, and that will come as a colored lines. Okay, and now those colored lines are called emission lights because it emits lights. It happens because of the emission of light. So that is why here we have written something like this. Yeah, the first one, this is emission spectra because of the emission of energy when the electron jumps from a higher energy to lower energy. So the same thing, if it goes from the lower energy to the higher energy, it has to absorb energy. So that is why it is called an absorption spectrum. I hope it is clear. I will show you some diagrams. So it is something like this. So the electrons can jump from a higher energy to a lower energy so that it can emit. Okay, and if you want to calculate what is the light, what is the frequency of light, then you can use this equation, that is delta E is equal to h nu. So you have to calculate what is the energy difference in between these two levels, and nu is the frequency of light, h is the Planck's constant. Just leave that equation anyway, just since it is written there, I am just explaining. Okay, so that is how it is happening. So that is the reason behind the emission of lines, or emission or absorption spectra, basically the reason of spectra, because the electrons are in different levels and the electrons can jump in between the levels, and during that jumping, if it is from a higher energy to lower energy, it will emit light. If it is from a lower energy to higher energy, then it will absorb light. Okay, so that is the working of spectra. And why it is unique, that is another thing. The lines, the presence and absence of lines are okay, it's fine. Then why it is so unique? Because it is unique because the levels you can see. So for an atom, levels like this, for another atom the levels will be so different. That means maybe the first level is closer and the second level is at another gap. Okay, so the gap will be different. So first orbit here, first, then the next one is. So this gap in the orbits varies for different atoms depending on how many protons are here and how many electrons are there. That gap will vary. Okay, so each atom has its own levels. Okay, so the energy levels, that means the levels at which the electrons are orbiting, is unique for each atoms. So that is why each atom has unique levels, means the jumping will be unique, the energy emitting or absorbing will be unique, so that the patterns will be unique, the spectra is unique, so that we can call it as the fingerprint. Okay, so now let's take the case of hydrogen. So in the case of hydrogen, I am just giving you an example of hydrogen. In the case of hydrogen, these lines has a certain name. So when the light is coming, electron is coming to level 1, okay, that means from 2 to 1, 3 to 1, 4 to 1, 5 to 1, something like that, all those lines, if it is coming to 1 or if it is going from 1, that series is called a Lyman series. So the next one, if it is coming to 2 or going from 2, it applies in both direction. Okay, and those lines are called Balmer lines. Okay, and this is passion, this is bracket, then fund. There are many series are there. So these are all the series. So you can see Lyman. Lyman is actually in the ultraviolet color. Okay, or we cannot see that. Balmer is the only visible one. Even though the ultraviolet is not visible, we can actually using spectroscope we can see it. Okay, because we have sensors for. Balmer is the visible spectral series for, or the series of lines in hydrogen which is visible is Balmer. Then all the others are infrared. So just with the hydrogen itself, it can give all this kind of lights. Okay, so these series are also unique. Okay, so these names are only for hydrogen. Okay, if it is helium, the first set of lines when it is coming to 1, it is not called Lyman. So Lyman, Balmer, these names are only for hydrogen, not for any element. Okay, because that is the most studied atom and because it's the simplest atom. Okay, so that's about it. Now let's see. So that is the purpose, or that is one usefulness of this spectroscopy, or by analyzing the fingerprint of atoms, we can say what are the objects there, or what is the constituents of this. And not only that, apart from the what is there, we can even say that relatively how much fraction is there. This much percentage is hydrogen, this much percentage is helium, or something like that, that the fraction of the constituents can also be determined from the spectrum. Okay, that needs some deep physics and some deep equations are there. So using that, actually we can find out how much or what is the fraction of those elements that are present. So all these things can be found out using just the light, splitting that light into its constituent colors. Now, other than that, even the spectra has another advantage. It can also be used to find out when an object is moving away from us or coming towards us, or at what velocity it is moving. Okay, and for that we use another phenomenon called the Doppler effect. So Doppler effect is simple. So Doppler effect applies to waves in general. So sound is a wave. So first it is observed in sound waves. So suppose that there is a car or something, a car or train with a horn, and which is coming towards you. Its sound will be, okay, the horn sound will be increased in pitch. Okay, it sounds at a higher pitch. Okay, and if it is moving away from you, it will sound in a lower pitch. Okay, so that shift in frequency happens because of the movement of that sound source. Okay, and that is called the Doppler effect. Okay, and this happens, this you may able to observe this in real life cases when an ambulance siren or something is moving towards you and away from you. You can actually notice this shift in pitch, not the shift in the sound, the volume of the sound. It is actually the pitch or the frequency. Now, since light is also a wave, this Doppler effect applies to it. Okay, so when a light is approaching you, a light source is light, not the light source is approaching you, its frequency will be shifted. Okay, and if it is moving away, again its frequency will be shifted. Let's see it one by one. Suppose an object is at rest. Okay, you can see it has a certain spectral lines like this, a certain lines, something like this. Okay, so that means that object you are observing, that astronomical object you are observing, okay, through a telescope or something, okay, through a telescope or something, and it is going through a spectrometer, and you got some pattern like this. Okay, now this, suppose this is a galaxy, and related to us, this galaxy is at rest or something, like if it is not moving at all with respect to us, there is the gap between us and the galaxy is not changing, then you got a pattern like this, and we call it as the rest or the original spectrum. Okay, or the rest spectrum. Now suppose if this galaxy is moving away from us, what will happen? Yes, you can see that the background colors are not changed, but you can see that with respect to that background colors, these lines, all these lines are actually shifted bit towards the red side. Okay, you can see it has to be supposed to be here, but it's shifted to the right side. Okay, when the object is moving away, the spectral lines will be shifted towards the red side, and that shift is called the red shift. Okay, now what will happen for the opposite? Yeah, now it is moved to the right. Now the other case, that is, if the object is coming towards you, again the spectral lines will be like this. The pattern won't change again, because it is here also you can see that the pattern is not changing. That gap between the lines are fixed, but the shifting is happening as a whole. Okay, so you can see here also the pattern is shifting entirely to the left side, when, or not just the left, since here it is blue in the left side, so it is shifting towards the blue side, so we call it as the blue shift. So red shift is observed when the object is moving away from us, and the blue shift is observed when the object is moving towards us. So from the red shift and blue shift, we can actually understand whether an object is moving away from us or moving towards us. But not just that, okay, not just whether it is moving away or moving towards us, we can even infer at what speed it is moving. Okay, so let's see, there is something called a delta lambda. So delta means, when it is used, delta lambda or something like that, lambda means the wavelength of the light. Okay, so, or wavelength of this particular. So a color means it corresponds to a frequency or a wavelength. So delta lambda means what is the difference. So delta you can read as difference. Okay, difference or change, something like that. So difference in lambda means the difference in wavelength is equal to lambda dash by minus lambda 0. So what is this lambda dash? Sorry, lambda 0. That is the original wavelength. Original wavelength means when the light was, or when the object was at rest. So there is no there is no movement in between the observer and the source. Then it is called a lambda 0. That particular wavelength. Now it is shifted. We are measuring that same line at another lambda. Okay, now it has to be here. Now it is shifted from here to here. Now what is this wavelength? What is the wavelength corresponding to this? That is the observed wavelength. Okay, and that is called a lambda dash. The difference is called delta lambda. So this is the observed wavelength, and this is the rest wavelength. Rest in the sense that there is no movement between the observer or our telescope and the source galaxy or the star or whatever it is. Okay, so we got this. So now we have the delta lambda. Now we can use this equation. Okay, that is delta lambda by, so delta lambda is so simple, you can find it as lambda dash minus lambda 0 divided by lambda 0. So that is delta lambda by lambda 0 is equal to v by c. What is here? V. So what is v? V is the velocity at with which the galaxy or whatever you are observing, maybe it is moving away from us or maybe it is coming towards us. That you can understand from the shift. If it is a red shift, it is moving away from us. If it is a blue shift, it is coming towards us. Now using this equation, now you have the lambda dash, you have the lambda 0. So lambda 0 is it. You can calculate this v. So simply rearrange this equation, c into lambda dash minus lambda 0 by lambda 0. And thing in this bracket, okay, lambda dash minus lambda 0 by lambda 0 is called the red shift, Z. So Z is a common term when you, especially when you learn about cosmology and all, you will learn the distance based on this high redshift galaxies or something like that. So that you will learn when you learn about the cosmology. So don't worry. So simple equation is this: V is equal to C into Z, but Z is this. So this is how we can find out the velocity with which a certain star or the galaxy or whatever it is moving. Okay, and also we can find whether it is moving away or below. Okay, now let's do one example of such a problem. So the question is like this: suppose a spectral line from a distant galaxy is observed at a wavelength of, so observed at a wavelength. So what is the observed wavelength? Yeah, lambda observed, lambda 0 or lambda observed, lambda OI is actually, that is 6650, and the unit is written as, properly it has to be written like this, called angstrom. Angstrom means 10 to the power minus 10. Okay, or just leave it, we can write it as angstrom itself. Here the unit is not a problem. So this is the observed one. Okay, now but its rest wavelength, that is the this is not lambda. Okay, sorry. So what was the convention? Lambda dash is the observed, lambda 0 is the rest. Sorry. Okay, so observed is lambda dash, so lambda dash is equal to, just a second, let me clear everything. Okay, so you can see observed, that is lambda dash is equal to 6650 angstrom, and lambda is equal to 6563 angstrom. What happens? This is the rest, and now the wavelength is increased. So wavelength, so this is 6563 and this is 6650. That means the observed wavelength is more than the rest wavelength. That means it is shifted towards the red side. That means this is a redshift case. Okay, so since this is a redshift case, we can say that already that distant galaxy is moving away. That is first inference we got from, even without any calculation. Okay, just by analyzing these numbers. Now what we want to calculate? We want to calculate the delta lambda. So what is delta lambda? Delta lambda is equal to lambda dash minus lambda 0. So 6650 minus 6563. Can you calculate it? Can someone calculate it? Or should I have to? 87. Okay, thank you. I hope it is correct. So 87 angstrom we got. Okay, so that is the delta lambda. Now what we have to do? We want to find Z. What is Z? That is delta lambda by lambda 0. That means 87 divided by 6563. Can somebody calculate and tell me the value? Or I can take the calculator. 87 divided by 6563. Yeah, I got it as 0.0132. Okay, I am taking only 0.013. So 0.013. Yeah. So this is the redshift. Now what was my equation? Velocity is equal to, that means the speed at which it is moving away or towards is equal to, yeah, it is not 0.13, it is 0.013. Yeah. Now V is equal to C into Z. What is C? C is the speed of light. What is the value of C? The value of C is 3 times. So let's calculate the V. So V is equal to 3 times 10 to the power 8 into 0.013. Okay. And what is the answer? Now, since the redshift is actually delta lambda by lambda 0, here it is angstrom, here it is angstrom. That is 10 raised to minus 10 will come here, 10 raised to minus 10 will come here, they will be cancelled out. So there is no need to change the units. So there is no need to put the 10 raised to minus 10 there. So leave it. So what is the final answer? 3 into 10 raised to 8 into 0.013. Anybody got it? So I will write it as 1.3 into 10 to the power 6 meter per second. Yeah, sorry, into 3. So 3 into 1.3 is 3.9 into 10 to the power 6 meter per second. So this is the speed at which that galaxy is moving away from us. That is a 3.9 into 10 to the power 6 meter per second. So this is how we can find. And how we know that it is moving away? Because the observed wavelength is more than the rest wavelength. If it was the opposite, then we can say that the same calculation will hold and we say that it is coming towards us. Okay, so that is from the shift. I hope it is clear for you. So that's it. I think there is nothing. Yeah, that is the final thing about today, and we have completed the first part of the session. Now tomorrow we will discuss about the stars and its life and how a star is born and how the death, something like that. Okay, so okay, so I will take some questions from the chat, then one or two questions. There is no need to put any more questions in the chat. There are existing questions that I will answer, and you can ask more questions at the direct question answer session. Don't worry, I will unmute each of you like what we have done. Sir, can this gas be a compound or a molecule? Yes, this is not just for elements. Actually, the spectroscopy will work for molecules or compounds, it will work, but for simplicity we have mentioned here as the elements. But for even that is how people actually find another organic molecules or anything, that is even in the chemistry. It is not just for astronomy. Okay, so any chemistry peoples who are working actually finding out in realistic scenario, not just in the labs by doing some tests, they are actually doing this spectroscopy to find out what compound it is they are made for, what molecule it is. So why do solids give continuous spectrum? Okay, solids, when it is heated up, it is something called a black body. Okay, so that you will learn maybe in your higher classes. I don't know whether it is sure. Anyway, that is called a black body. So this black body spectrum is something always continuous. So its reasons are all it's not now I cannot explain. So that is called the that heating. So when you heating a solid thing, that is actually giving off light and like a black body. So that spectrum is a continuous spectrum. And for liquids, so if you pass that continuous light through a transparent liquid, and again transparent in the sense need not be completely transparent. If you send some light through alcohol, if you send some light through some potassium permanganate solution, then also the lines will be unique. Okay, so it applies for liquids as well, and there are different kinds of spectroscopies. So when the electron jumps from lower energy to higher energy, what energy does it absorb? It is absorbing the light energy. Okay, so it is absorbing the energy from the light. That is why there is some missing light, or when it is yeah, there is some missing light. Okay, so it is absorbing light energy from the light. So that is why that light is, that some particular energy or particular color is absent. Okay, now let me unmute you one by one. So first of all, Kaivalya. Okay, now you can ask.
Sir,
Yeah.
I just had to ask. I think this was like from last lecture. Sir, can you just explain how many light years is parsec?
3.26 light years.
Okay, sir.
3.26
Thank you.
light years. Yeah.
I needed to ask you since last lecture. I didn't
Okay.
get
Okay.
it.
Yeah. Fine.
Thank you, sir.
Now Manomai Gupta, you can ask. Yeah, you can unmute and ask.
Sir, I just wanted to ask, can we get the notes of all this?
Not the notes. You have to note it down. The PowerPoints, the presentation will be shared at the end of the session. Means after Friday, it will be shared.
Okay.
Okay. Yeah. Notes you have to, in between these calculations or other things, you have to note it down. But the PowerPoints will be shared. Don't worry. Now, Ronit Suryavanshi. Okay.
Uh, Sir, you wrote here V is equals to 3 into 10 raised to 8 into 0.013. Why did you multiply it with 3 into 10 raised to 8?
Because that equation is like that. You just see that in the previous slide, then you can see if you want to find out this is Z. So the equation is something like this. Z is equal to, okay, v by c. So if you want to find the velocity, the z should be multiplied with the c. Z is the redshift that you have calculated. That is the 0.013 that you got, I'm sure.
We multiply it every time with 3 into 10 raised to 8, right?
Yes, yes, yes.
Okay.
Now, Krisha Desai, you can ask.
Sir, I have two questions.
Yeah.
What is diffraction? And in this question which you solved now, how did you
Your
decide
voice
that
is actually
it's
broken.
redshift?
It is not clear. It's not properly audible.
Hello.
Yeah.
I wanted to ask, how did you decide that in this question it was a redshift?
Okay. How I decided whether it is okay. Now one more thing you can see here. Just I will explain it here first. Let's go back and see this. Okay. Now if it is redshift, the question is, I know that is how I define whether it is a redshift or a blue shift. Okay. Before going to that, you can see that you can see this band of colors that start from violet to red. Okay. And the violet has the lowest wavelength. Okay, so here wavelength increases in this direction. So that means the red has the highest wavelength and the violet has the least one. Okay, so now this is the rest wavelength, or we call it as a lambda 0. Now the lambda 0 should have been here, and the corresponding line is actually shifted to this side towards the red side. Means what will happen? In this direction the wavelength will increase. So this lambda dash, this is the lambda dash that is observed one. So the lambda dash is more than the lambda 0. That means the wavelength of the rest one is more than the other way. Okay, so the observed wavelength, that is the lambda dash, is more than the rest. That means it is a redshift. Okay, then only it can shift towards the right. So just example, you just imagine this is the reference one or the rest one. If it is shifted towards the blue side, that means it has a shorter wavelength or it is a blue shift. So if it is a red shift, the wavelength will increase. Okay, so if the observed wavelength, so observed wavelength is more than the rest wavelength, it's a red shift. This is a red shift. You can note this actually. And if the other way, the observed wavelength, okay, is less than the rest wavelength, then it is a blue shift. Now if it is a blue shift, you know that it is coming towards you, and if it is a red shift, that is moving away from. Okay, let's see this question once again. Just see what is the lambda dash. This is the observed 6650, and this is lambda 0. So lambda dash is greater than lambda at rest. So observed is greater than the rest. That means this is a redshift. This is how we understand whether it is a redshift or blue shift. Hope it is clear.
And okay, what is diffraction?
I didn't get. Can you repeat?
Diffraction.
It's not clear. Can you just put that in the chat?
Yes.
Yeah, it's broken. That's why. Yeah, I will take your question from the chat. Don't worry. Okay. So meanwhile, you can put in the chat. Meanwhile, Dhwani Bhatt can ask the question. Krisha Desai, you can put your question in the chat. Dhwani Bhatt, you can ask. Yeah.
Yes, sir. My doubt is, you told that we have the grating thing or prism inside a telescope. What is its significance? Why?
That is all the whole point of this lecture. because then only we can split the light into different colors, and we can find out is there any missing color is there. Then we can find out, okay, this element is there, and if it is a red shifted or blue shifted, at what velocity it is moving, and those things can only be analyzed by splitting the color light into different colors. So to split the colors into different or the split the light into different colors, we need to put a prism or a grating inside the telescope, or simply we need a spectrometer along with the telescope. So all the telescope has this thing. Okay. Now, Krisha, you haven't put the question there. You can put it in the chat. Now, sir, can share all the equations clearly in the group. So you will get the final equations, especially from the PowerPoint, that you can take. Other equation that you should note down. If anything I have mentioned, then you have to note down during the class. What was the name of the triangle mirror? It is not triangle mirror. I will show you the picture of that, the real picture of that. Some physics. So this is the actual shape of that thing. Okay, you can see this. So this is the prism. Okay. Oh, what is diffraction? Okay, so diffraction is kind of what to say, when light pass through some hindrance or some block, then the wave will interact with each other. Okay, so it is because of the wave nature of light, the light get interact each other, and some superpositions will happen. So the light can mix together. Different lights will split into different colors. That is something. How will I explain that? For example, so it happens even in the waves actually. So diffraction of waves, not light, waves. I will show you some pictures here. So you can see that, yeah, here you can see two types of lights are coming from here. Okay, so it is just to denote that. So imagine this as not the light, just imagine some waves in a water tank or something. There is two blocking, and when it comes through these two slits, actually these lines are the peak of that wave. Okay, now when those lights are mixing or those waves are coming together, there is something happens, that's called a superposition, or the addition of waves will happen, and at this points there will be a bright peak, and the other point there will be a depression. Okay, or the low wave will be there, or the light is minimum. So that mixing of wave or the superposition of wave is actually called the diffraction. Maybe you will learn in higher classes. In schooling you will learn. Okay, or you can see it can define it in different waves, and that is when there is a wave is there, you can see that when this wave passes through a small hole, actually since it is a wave, this wave will actually spread into other area, even to the shadow area. Okay, so now let me take some questions from directly. So Tushar, you can ask the question.
Yes. Sir, actually, I had a question that what is the value of z in the equation?
3 into 10 raised to 8 meter per second. Okay, so
Okay,
3, that is the velocity of light, speed of light.
Sir,
3 times 10 to the power 8 meter per second.
sir, what do we call that z?
Z. This Z.
Yes, sir. Sir, what do we call it?
Redshift. That is properly the redshift.
Okay, sir.
Now Yash Dorug. Okay, Yash, you can ask. Okay.
Sir, I was having two questions.
Yeah.
Sir, what special property is the prism having that it causes the diffraction of light?
Okay, that special property is that its shape is basically the reason. If it is a single glass slab, something like this, okay, which has the same size at both sides, the light can come inside and it will actually cause something. It will go directly like this. So that is why we are not observing it for usual things, okay, or usual light. But in usual glass pieces, we won't observe this Vibgyor like coloring, okay. But in the case of a prism, now even in this case, actually, when the light enters a medium, especially slantingly, the light gets bent, okay, and that bending will occur on the basis of the wavelength, okay. So the light which has, especially if you take the case of the red will bend less, and at the same time the blue will bend more. But usually that bending will happen here as well, but since it is a thick glass piece or something like it is parallel, when it comes out together. But when you make it shape in a unique shape, not only this, even for spherical shape and all, this will happen, okay. It is not just for the triangular shape is a perfect example for the prism. So when the light comes here the red will go through a small shift and the blue will shift more. And the reason for this shift, or why red is shifting less and the other is shifting more, because each of this color, okay, or each of this light has different velocity or different speed for this light. So we are not talking about the speed of light in vacuum. Now we are inside a glass or something like that. We are inside a medium. Each light has its own speed, or each color has its own speed, and because that each of them will bend at a different angle, and since the shape is like this, they will actually won't come as together inside. It will actually split into its constituent colors, okay. So that is why it is happening.
Sir,
Yeah.
and my second, I got your point. And my second question is, can I get the value of Planck's constant?
Planck's constant 6.6 something into 10 to the power minus 34. Just check exact value. I will check. Okay.
Yes, sir. Thank you. Thank you, sir.
Yeah, sure. Planck's constant value. Yeah, 6.626 into 10 to the power minus 34. I only remember this 6.6 into minus 34. Okay, so that is the value of Planck's constant, 6.626 into 10 to the power minus 34 joules per hertz, okay, or joule second. So now, yeah, Sri Mahitraj can ask. Sri Mahitraj.
Sir, I have two doubts.
Hmm.
One is that, can you explain me the Doppler effect, sir? Doppler effect.
Okay. Then what is the other question?
Sir, Z is equals to means red shift minus Z means a blue shift analysis.
Yes, exactly. Yeah.
Yes.
If Z is positive, that's a red shift, and Z is negative, it is a blue shift. Now you want the explanation of Doppler effect. Okay. So yeah. So the explanation of Doppler effect is that the shift in frequency. Basically, if you say it generally, when a source of wave is moving, okay, when it is at rest, there is no Doppler effect. When there is a movement, okay, between the source and the observer. So observer is someone, whether it can be any type of wave, okay, it can be sound wave, it can be light wave, it can be even the water wave. All this case actually Doppler effect will apply, and but it is most important and prominent in the case of light and sound. Okay, so when the light or the some wave is there, and there is a source of wave is there, and we are observing it. So when there is a movement in between the source and the observer, okay, when it is moving away from us, or then there will be the wave will shift to a lower frequency, and when it is coming towards us, it will shift to a higher frequency. So that frequency change in wave, because of either we can call it as a frequency wave or the wavelength change, okay, because we can connect it through a simple equation. Either we can call it as whether it is frequency or what is called the wavelength. So the shift in frequency of a source of wave, or shift in frequency of a wave because of the motion between the source and the object, or the source and the observer. Okay, so the shift in frequency of a wave because of the movement or the motion of the between the object, the source and the observer is called the Doppler effect in general. Okay, in the case of sound, that shift in frequency appears as the shift in pitch, or in case of sound, frequency means the pitch, and in case of color or in case of light, frequency means the color. So shift in frequency means there will be shift in color. Okay, so that is what is happening. So in the case of equation, either we can represent it in terms of wavelength or in terms of frequency. That is not at all a problem, especially in case of light. The frequency and wavelength are connected by this equation. F is equal to c by lambda, or you can rearrange it at whatever way you want. No, don't worry about it. Okay, so it can be easily connected. So this is generally the Doppler effect. Okay, so that shift in frequency of a wave because of the motion between the source and object is called the Doppler effect, and it applies to any waves, especially in astronomy. It is important for light. Now, Yok, Thakkar, you can ask.
Yes, so I have a doubt. Then, when we are seeing a planet from far away, to know whether it is redshift or blue shift, right? But we are also moving. So, with respect to that planet or with respect to us, the planet is either moving away or it is moving away and towards, right? So, how can we determine it is only redshift or blue shift?
Yeah, okay. So that we observe it for a so since okay, suppose there is a planet. Usually this is one thing that people do, especially for planets, especially for the detection of extrasolar planets or exoplanets. So there is a star, okay, and a planet around it. Okay, this is the case. But the problem is that we cannot even see the light from the planet. Okay, so because the star is so bright, so that we cannot see the planet. Now, what they do is that, and another interesting thing. So when there is a planet like this and a star, actually they are orbiting. We say that the planet is revolving around the star, but it is not that correct. If you look it closely, actually both the star and the planet, okay, are orbiting about their common center of mass. Okay, so there is a balancing point of their mass, and about that point it is actually moving. So in that case, the star is actually not perfectly, the center of rotation is not or the revolution is not at the exact center of the star. So this star will make a wobbling motion. Okay, it will make a wobbling. So it will be moving like this. Okay, so that wobbling motion, when it is going like this, or if I exaggerate that, that star itself make a small circle. Okay, so now I am observing it from Earth in this direction. From here I am observing. Okay, now when the star is going away from you, okay, in this direction, it will show a red shift, and when it is coming to you, it will show a blue shift. So from this we can infer. So if you observe that spectrum, okay, of the star, okay, so suppose that, and there is a problem, as you mentioned, the Earth is not stationary, it is also moving. Okay, but even if the Earth is moving, okay, this period we know the period at which the Earth's rotation is happening. Already we know that rotation revolution will happen in some 24 hours, in 365 days. So we know that what will be the shift or the change in blue shift and red shift, the alternate blue shift and red shift, if there is only Earth is moving. So, but apart from that movement, we can actually distinguish what is the movement of this star. Okay, so that will also repeat that pattern of red shift and blue shift. Okay, so it will be a pattern which is actually the red shift and blue shift repeating periodically, and from that actually we can infer, or we can separate out the movement of that star. And there is another interesting thing about this. For example, sun is here. So and we know that the sun is self-rotating. Okay, so sun has a rotation. Actually, scientists find out that one method is by observing the sunspot. We can infer that it is rotating. And another method, if it is rotating like this part of the sun is actually coming towards us, and this part is actually moving away from you. So even here we can observe the red shift, and here, sorry, here you can observe the blue shift, and here you can observe the red shift, and from that we can infer the sun is moving at what velocity. We can measure the rotation velocity of that.
Thank you, sir.
So now Anushka, you can ask.
Sir, so my question is, for the line spectrum of gases, what if you use an isotope of the gas? Like, what would that change in the line spectrum?
That will also change. I don't know exact change what it is, but even if it is an isotope means there will be change in the neutron number, maybe. Then if it is ionized, something like if you take the hydrogen spectra, that is H hydrogen spectrum mean two electrons are there. Its spectrum is actually different from an H plus atom, or that means if one electron is removed, even then the spectra will change. So that much sensitive the spectra is, even at the minute change. And the spectrum of hydrogen, if you take the hydrogen alone, its spectrum is unique, and the hydrogen is there in the water itself. So if you take the spectrum of water, or maybe from that if you take the hydrogen spectrum, is different. So presence of a nearby more atom also change the spectrum. So the spectrum is so sensitive, but it is again unique. So that is how we can the molecular spectra, and there are many kind of spectrums are there, not just by the shifting of or the transition of electrons. So there are some other vibration that is happening for atoms. For example, if you take the H2O, so H and O. So actually these are all the bonding or the connection between the molecules or the atoms. That is how we have this. And this movement, this is actually not a something like a stick. It is something like we can imagine at a rubber stick or some elastic thing, so that this molecule can vibrate. Okay, something like H can come here and go back. Something like a vibration is there. So that is a unique frequency, and based on that frequency, that is even detectable using some kind of spectroscopy, and we can say that hydrogen or water is there. Okay, so there are many kind of, and the atoms can rotate, and based on that rotation there are different kind of energy, and based on that energy we can distinguish what it is there. Okay.
Okay, sir. Thank you.
Okay, I hope so. I think there are no more questions. If anybody has any questions, even you can ask a question. Or let me check the time before. Yeah, we have 7 more minutes. You can ask question. Okay. Is there any more question? Yeah, Krisha Desai once again. Yeah.
So how do we know the wavelength by streamer spectrum?
Can you repeat?
How do we know the wavelength?
Do we know the wavelength?
Just by looking at spectrum, how do we understand what is the wavelength?
Okay, just by looking at the spectrum, we cannot understand what wavelength it is. So for that, actually, one thing that we do is that the spectrometer. So we have some standard spectra, or using that spectrometer, we can observe it, and based on the what is there on the that grating or prism, and by standardizing it, we can actually find out what are the specific lines are there, or what is the wavelength of a certain line. That is one thing that we know. But in astronomy, that we already have all the spectrum of all the popular or the most important elements. All the elements are there, and especially for astronomy, in the case of we know just a second, I'll show you that actual spectrum. Okay, so in this actual spectrum, you can see that we already know the hydrogen spectrum. Okay, so what we do is that we assume that this is one line from the hydrogen. Okay, then we know that after certain distance, you can see that at a certain gap, okay, we have to observe the H beta line. Okay, so then if we choose this as the H delta, for example, I'm choosing this as the H delta. Okay, so H delta is delta means a Greek alphabet to specify a certain line, so don't worry. And I am assuming that this is the H delta. So if this is the H delta, then towards the right, after this distance, after a certain distance, I should find the H beta. So that I know from lab results. Okay, that is I already have the hydrogen spectra. Then I look for after that certain gap, is it there? Okay, like if I cannot find, if I can find, then I assume that that is the H beta. Then I look for another one, H alpha, that should be at a certain distance. If I can find, then I will check one or two more. If I can find it properly, then I can say that that is the hydrogen spectrum. Otherwise, the problem is that here in this case, if I choose this as the hydrogen H delta, then after that same gap, I cannot find a spectra corresponding to hydrogen. So then I will choose this line, and I say that, then I look for this, then I find this. So that is by comparison that we assume one line as a certain line, then look for the others, then by that we can calibrate. If I get at least one spectra of hydrogen or anything, then I got the hydrogen correctly, then I can easily find out what the other wavelengths are exactly. And from the pattern or the gap, we can actually get the okay. Okay. Yeah, and there is some more. Debargaya Chakrabarti. Okay, you can ask.
Sir, I have a question that though light has a particle nature, so how it emits light means electron emits light when it when it comes from higher state to lower state and releases energy, and it comes from as a light.
Yeah, light is first of all, light has both the nature, that is, it has the nature of particle and it has the nature of what is called the wave. Okay, so both nature is there for light, and even if you consider it as a particle, okay, no problem, or if you call it as a photon, even though it is a form of energy. Okay, so when something is transferring from one energy level to another energy level, it is emitting that energy. So energy can be emitted in different forms, and when the electrons are transferred from one level to another level, that energy is emitted as light. Okay, so that's just, so you can imagine it as a wave or a particle. That depends on which context it is. So light can behave in both ways. We cannot call it as a particle or a wave. It is something else actually, but it is something else, but it has both the characters. Okay, so now Anushka, you can ask.
So like suppose for line spectrum, we take a gas which has a fluorescent emission, and when we do the line spectrum technique for it, like will we be able to distinguish between the fluorescent emission and the line spectrum, or like it's
Yes.
obvious to be distinguishable?
Yeah, it is. It is actually whatever kind of spectra it is there. So each of them will be distinguishable. Okay, that won't be a problem at all. because we have the standard things are there. We have elements are there, and for all the elements we have done the spectrum. So just Google for any spectrum. You can, if you want to see the spectrum of calcium, just Google for that. You can see the even in the Wikipedia itself it is there, I think. The spectrum is given there. So that is a standard spectrum. Then that standard spectrum we can say, it is not just for the certain elements, for molecules, compounds, all we have the standard spectrum. So it is something like a database of a police. Okay, so a police department will have a database of all the suspects or the criminals already there. So it is like that. The scientists have the database of all the spectrum. Okay, so once it is there, they can find it out. But there are events when there is no database is there, like the case of the real uh, uh, crimes and all. So that is one example. When the sun spectra is analyzed, the people find out one unknown element. So they were able to figure out hydrogen, calcium, oxygen, that are all fine, no problem, but they weren't able to find out one special spectrum. Okay, and that means it is a something else unknown. We don't know what it is, and it's not there in the periodic table as well. So then people later detected an element called helium, and then compared its spectrum with what we already discovered in sun. So from that comparison, they were able to find out that is a new element, and they named it in the name of sun. That is why the name helium. Okay, Helios means sun, so that is why the name helium is. So now Dev Kumar, you can.
Good evening, sir.
Good evening.
Sir, may you please tell me the proof of Doppler effect equation?
The proof of Doppler effect equation, that is actually quite difficult to explain because it needs some relativity and all. Okay, so it is not just a simple equation, even though it looks like just V by C is equal to something, but its actual derivation comes from the relativity, Einstein's special relativity. So that is we cannot learn right now.
Yes, sir.
Okay.
Thank you, sir.